Do not try and bend the spoon. That's impossible. Instead, only try to realize the truth.
What truth?
There is no spoon.
There is no spoon?
Then you'll see that it is not the spoon that bends, it is only yourself.
So where has this pursuit taken you?
Oh my God.
Where have you landed?
Why would you ask that?
I'm asking you that here and now. It's New York City. It's March 7th.
Well, partly it's taken to these very strange images that are behind your head right now. These are pictures of equations. I've been, for the last 15 years, trying to answer the kinds of questions that my colleagues here have been raising. And what I've come to understand is that there are these incredible pictures that contain all the information of a set of equations that are related to string theory. And it's even more bizarre than that, because when you then try to understand these pictures, you find out that buried in them are computer codes, just like the type that you find in a browser when you go surf the web. And so I'm left with the puzzle of trying to figure out whether I live in the Matrix or not.
Wait, you're blowing my mind at this moment. So you're saying, are you saying your attempt to understand the fundamental operations of nature leads you to a set of equations that are indistinguishable from the equations that drive search engines and browsers on our computers?
That is correct. So,
wait, I have to just be silent for a minute here. So you're saying as you dig deeper, you find computer code writ in the fabric of the cosmos?
into the equations that we want to describe the cosmos, yes.
Computer code.
Computer code, strings of bits of ones and zeros.
It's not just sort of resembles computer code, you're saying it is computer code.
It's not even just is computer code, it's a special kind of computer code that was invented by a scientist named Claude Shannon in the 1940s. That's what we find very, very deeply inside the equations that occur in string theory and in general in systems that we say are supersymmetric.
Time to go home, I think. Where are we going to go? So are you saying we're all just, there's some entity that programmed the universe and we're just expressions of their code?
Well, I didn't say that. Some of those,
like the Matrix? That's what you said.
Some of those codes are showing on the screen behind you right now. They don't look like codes, but these pictures, which we call adinkras, are graphical representations of sets of equations that are based on codes. So this is, in fact, to answer your question more directly, I have in my life come to a very strange place because I never expected that the movie The Matrix might be an accurate representation of the place in which I live.
The world's first programmable computer, the Zeus Z1, was able to perform 2 flops or floating point operations per second. Modern computers do this 27 trillion times faster, and this has been achieved in a mere 79 years. According to scientists, the power of computers will grow several million times more in the next 100 years. It's hard to even begin to imagine what kind of world our children and grandchildren will live in. Already, virtual worlds, like the one, for example, in Grand Theft Auto, shock with their detail. It's easy to imagine that they will become indistinguishable from reality in the next 50 to 100 years. In fact, it's possible that we will be able to create virtual universes in which the characters really think and have minds similar to ours, but won't know that they live in a simulation. This is frightening on many levels. And what if we are such characters already? What if the whole world that you see outside the window is a simulation? Philosopher Nick Bostrom first introduced the general public to this hypothesis regarding the virtuality of our world back in 2003. Its essence was that if many technologically developed civilizations exist in our universe, then it is likely that they can create simulations similar to those in which you or your children play sitting at your computers, only millions of times larger and more realistic. This means that you or I could be in the role of an NPC, a non-player character, in some alien sandbox right at this moment. And people really are taking this seriously. Elon Musk, for example, said in 2016 that there's only one chance in a billion that our reality is not a simulation. When you hear such a thing from somebody like Elon Musk, serious doubts regarding the nature of our reality begin to arise. This forces us to at least begin a serious search for some kind of answers. And this we will do now. Evidence of our virtuality. Grand Theft Auto 5, also known as GTA 5, is a very good example of how all this could be accomplished. In the game, on one of the many streets of its virtual city called Los Santos, you see a very familiar picture. You are surrounded by cars that are hurrying to and fro somewhere into the distance, and crowds of people line the sidewalks. In general, everything's very similar to how it is in real life. And in the game, this general picture accompanies you everywhere, all the time, regardless of your location in Los Santos. If you turn a corner, you see more cars and more crowds of passers-by. So, being on that Los Santos street, you might think that the same story is happening to others, that life is alive and happening in the whole city at any point in the urban landscape. But, in fact, this is simply not true. You must not forget that everything you see is just an illusion, built just for you. While you are on the street with the conditional name A, absolute nothingness has filled Street B. Nothing happens there. The game continuously, magically draws for you this living, active life, while Street B drowns in silence and, in fact, barely exists. All modern video games work on this principle. When you are absent from a certain location of a virtual city, there is absolutely nothing at this location. No people, no cars, no city itself. The developers optimize the game in order to reduce the load on the computer hardware. Thanks to this, you can enjoy such incredibly realistic graphics and in-game physics that are the modern masterpieces of the gaming industry. If a player, or rather a character, turns and looks at something, the computer makes the image in front of him as detailed as possible, and the textures and objects behind the player's back, that is, out of view, become as simple as computationally possible, or really disappear altogether, except as a potentiality. As we said, this allows the computer to reduce the load on the game platform while maintaining beautiful graphics. If you look at the location from on high in GTA 5, the whole city will look as if it is in the palm of your hand, and you will see how cars are rushing up and down all of the numerous streets. So, does that mean the power of a console or computer is enough for such a complex and detailed picture? Let's not jump to conclusions. The fact is that the physics of the game also get simplified for objects like cars that are far from the observer. If we fire a rocket into such distances, we can barely see it explode. If we fly closer, then the explosion looks much more detailed and realistic, and requires far more computer power. The next example is the game Civilization 5. If you quickly move the camera from one end of the map to the other, you will see the location loaded right before your eyes. The game engine is not perfect, so we can see how the view responds to our actions, realizing that we are looking at it. That is, the observer influences the game world by the very fact of his or her observation. This is how any video games of the future will work as well. Even if super powerful computers can simultaneously calculate all the more or less large objects in a large location, Even over many years, small details will remain to be rendered. Flies, blades of grass, and yes, even microbes, of which there are quite a few. All of which will be loaded only under the gaze of the observer player. Everything is for the sake of optimization. So, after that gaming preface, we now move on to the first proof of the theory that we are living in a Matrix-like simulation. You may know about or remember one of the most famous experiments in the history of physics, the experiment of Thomas Young, the double-slit experiment. It was a real coup in physics and led many scientists into the study of quantum mechanics. If you throw solid balls at a shield with a slit cut into it, a single diffuse strip designating the strike points will appear on the screen behind the shield. If there are two slits in the shield, then there will be two strips. But how will waves behave if aimed at the shield? They will pass through the slot and spread out. The greatest impact of the waves will be in the line of the slit, as in the case with the balls. But if you add a second slit, everything changes. A number of alternating interference strips will appear on the projection screen. And when we shine light on the two strips, this is exactly what happens. And this is how Mr. Young proved the wave theory of light. If light were corpuscular, like a particle, instead of wave-like, it would behave like the balls, and the screen would show two strips of light corresponding to the two slits. That didn't happen. Later, it turned out that electrons and protons behave exactly the same way, showing that they also seem to exist as waves and not as points. There was one assumption that perhaps light and the others were particles, and that somehow the particles bumped into each other and flew apart. So, to test this, physicists decided to shoot electrons at the target one by one, single file. And what do you think happened? The strangest thing imaginable. The interference pattern still appeared on the screen. It seemed that the single electrons somehow divided into two waves, passed through both slits, then interfered with themselves. Impossible. So physicists tried to find out through which gap the electron actually passes. They installed measuring instruments to check this. Another seeming impossibility occurred. The electrons stopped behaving like waves and began acting like particles, and left a trace on the screen of two distinct strips, with no interference. They had to admit something completely mind-blowing. That the fact of our observation or measurement destroyed the wave function of the photons, causing them to become like points, corpuscular. The electron, under the influence of observation, behaved like a particle, flying through one slit and not through two. Interpretations. Well, it certainly looks like the work of a game engine, doesn't it? This might make you think that our world is running like a game on a computer. The computer's power is not enough to calculate the motion of each and every particle, so it uses a simplified model and applies precise calculations only if an observer needs to look at the particle, so as not to break the illusion of the reality of the world for the observer. Such an explanation could not have occurred to people from the past. The results of Thomas Young's experiment were published in 1803, when it was impossible to even think about virtual reality. There were many theories suggested for just what the heck was going on, and the most famous of them, the Copenhagen interpretation, was proposed in 1927. Niels Bohr and Werner Heisenberg suggested that elementary particles are both waves and particles. To measure an electron, it is necessary to strike it against the screen of the measuring device. The wave functions of the electron collapse when it is measured, and it becomes only a particle. And this means that it is not exactly the observer, but the measuring device that influences the result of observation. But if this theory is correct, it still does not discount the hypothesis of the simulated matrix world. For example, a programmed photon could propagate in the network as a wave and restart when the node is overloaded, turning into a particle. This way, one can explain both quantum waves and the collapse of the wave function. The second most popular explanation of the behavior of particles is the many worlds interpretation. To greatly simplify, it looks something like this. We can assume that there are parallel universes in which the same laws of nature operate, and for each act of measuring a quantum object, the world splits into several versions. Each of these versions sees its own measurement result and acts according to it in its universe. In the eyes of the layman, this is a strange explanation. But it's a free world, at least we think it is, and so anyone can decide which interpretation they like best. In a poll of physicists held 20 years ago at a symposium under the auspices of the University of Maryland, 13 voted for the Copenhagen interpretation, 8 for the many worlds theory. Several other scientists chose other, less popular options, and 18 participants opposed all known interpretations. Disputes are still ongoing. In 2006, scientists conducted a more sophisticated version of the two-slit experiment, this time with a deferred choice element involved. In simplified form, it goes something like this. Particles are again shot through a barrier with two slits in it, but this time the observation of which slit they pass through is made at a time when the particles have already passed through the slit, but have not yet hit the projection screen. Like an observer who only opens his eyes after a certain moment. And can you imagine this? The electrons behaved like particles at this moment, as if nothing had happened from the moment of their launch from the electron gun. As if they did not pass through both slits and did not represent a wave. It seems the particles knew that they would be measured before it ever happened. The second proof. The next hint at the existence of a matrix can be arrived at from the maximum speed in the universe, the speed of light. Einstein explained that nothing could move faster than photons in a vacuum. The speed of light is a limit and a constant. Additionally, the faster an object moves, the more time slows for that object. At a speed of 300,000 kilometers per second, time stops altogether. That is, you could get to distant galaxies, let's say 3 billion light years away, in the blink of an eye on a spacecraft that had such a speed, according to your time, of course. Those same 3 billion years would pass for a terrestrial observer. So, time for a photon stands at 0. It cannot accelerate faster. For this, it would have to slow down time even more, which is impossible as time has already stopped. But why do speed and time have such a relationship? Why are space and time interrelated? The answer suggests a virtual world. The matrix hypothesis assumes that the speed of light is a product of information processing. That is, the world is being updated at a certain rate. It's 1 trillion times faster than any of our supercomputers now, but the principle is the same. Time slows down with an increase in speed. Because virtual reality depends on virtual time, each processing cycle is one tick. When the computer slows, the playing time also slows down a bit. This is very similar to the way in our world that time slows down with increasing speed or near to massive objects, which points to the possible virtuality of our universe. It can be assumed that in a ship that rushes with tremendous speed, the processing cycles of the system hang for the sake of saving resources. The third piece of evidence. The most serious proof that we live in a matrix simulation is quantum entanglement. Well, what is it exactly? A photon flying through space can be considered to be rotating. That is, it has something called spin. In fact, photons don't really rotate, but this is a simplified model. So, physicists believe that, most likely, before a particle is observed, it does not even have a specific spin. That is, no one is looking at the photon yet, so it cannot determine which way to turn, and is considered to be in a superposition of uncertainty. It would seem that it's difficult for nature to calculate the rotation of each and every particle, and so it uses a simplified scheme for this. But, again, when an observer appears, the particle becomes physically more complex and more real, and its rotation is calculated. An experiment was proposed by Albert Einstein, which was to test the Copenhagen interpretation for strength. Some very interesting results were obtained from this experiment. The essence of it goes like this. If an atom, for example, cesium, emits 2 photons in different directions, then because of the law of conservation of momentum, their state will be interconnected. If one of them rotates from the bottom up, then the other will rotate from the top down, always. They will always have spin in opposite directions. This is called quantum entanglement. But Remember, the photons do not know which way to spin before they are observed. So in this case, if the fact of observation made one choose one of the options, its tangled partner must then immediately have a spin in the opposite direction. That is, by the very fact of our observation of one photon, we affect the spin of the other photon, even though we did not observe the second photon. And the second photon is required not only to find a spin, but to do so instantly, even if the photons are at a great distance from each other. That means that if the entangled photons were somehow sent even to different ends of the universe, this information about which way it should be spinning should somehow fly or jump across the universe to its partner at several quadrillion times faster than the speed of light, so that it basically instantly gets its spin. This is incredible. It violates the very laws of physics as we know them, because nothing can move faster than photons in a vacuum. However, the second photon still manages somehow to get this information in zero time. But how? How does the partner entangled photon learn with such speed that a colleague was observed, and so know to spin in some particular direction? Einstein was convinced that such an instantaneous connection was impossible, and he assumed that when entangled photons emerge from the atom, they already contain information about the past and know which direction they will rotate if or when they are observed. That is, the observer does not change things but only recognizes the spin of the particle. But 17 years after Einstein's death, it turned out that this singular, unparalleled genius was mistaken in this case. That's right, Einstein was wrong. To prove the presence or absence of information about the direction in which the particle rotates after observation, Irish physicist John Bell set up a very complex and ingenious experiment. The results were astounding. Bell proved that the entangled particle does not have a clue before it is observed in which direction it will spin. The photon randomly chooses a spin only after measurement. And this is proof that entangled elementary particles can transmit information to each other much faster than the speed of light. The experiment gave us more new questions than answers. In 2008, a group of researchers from the University of Geneva decided to clarify the speed of information exchange between entangled particles. They were able to separate from each other two entangled photons at a distance of 18 kilometers. They measured one particle and recorded how fast the second reacted to it. The technology they used allowed them to measure a delay time of up to 100,000 times faster than the speed of light. But there wasn't even such a minuscule pause as this. It turned out that, as measured, the photons somehow were able to transmit information at least 100,000 times faster than the speed of light, and maybe even instantly. Perhaps Einstein was right when he said that instant communication in the physical world is impossible. But if we substitute a virtual reality in place of the physical world, the instant connection is easily explained. When two photons become entangled, their programs are combined to jointly see the 2 points. This combination of programs will respond for both pixels, if we can call them that, no matter where they are. At the moment of measuring one particle, its program randomly chooses one of the spins, and the program of the second immediately reacts. It becomes clear why the distance isn't important. The processor does not need to go to the pixel to ask it to spin, even if the so-called screen is large, even as large as a universe. Physicists say that no one really understands quantum mechanics, but if we assume that our world is virtual, everything quickly becomes quite clear. To describe the world of elementary particles and their interaction, scientists use quantum mechanics, and for the macro world, Einstein's general theory of relativity is used. But if these two worlds coexist in nature, then a theory must exist that would allow for both. And this is exactly what the hypothesis of simulation does. It perfectly explains this. The mysteries of the Big Bang, the curvature of space, the tunnel effect, dark energy, and dark matter all can be explained on the basis of the assumption. They say this simulation theory, even if confirmed, wouldn't change anything. But official confirmation could strongly spur new research and, perhaps, scientists would be able to find new shortcomings in our world, and they could be used to create new technologies. For example, if quantum effects are caused by the virtuality of the universe, the creation of quantum computers or quantum cryptography can be called the use of the conventions of our world. Are we in a matrix? New, indirect hints that we live in a matrix are discovered every year. At such a rate, in about 30 years, the virtuality theory of our world could become as official in the world of science as the theory of evolution today. Perhaps it won't be too long until they teach in schools that we live in a virtual world. Although it is somewhat demotivating, realizing that you might be just a complicated program with feelings and self-consciousness. Elon Musk believes that, on the contrary, it would be good news. The simulation hypothesis solves the Fermi paradox and shows that intelligent civilizations are able to avoid self-destruction and technologically grow to achieve even the creation of virtual worlds. So, life in the Matrix for Mr. Musk is a pretty decent utopia. He wants this to be true. By the way, recently the famous scientist Neil deGrasse Tyson and some of his colleagues spent several hours debating the topic, is the universe a computer simulation? Be sure to watch it. If you like this topic, I advise you to see the film The 13th Floor and, of course, the Matrix trilogy. And don't forget...
This is the Illustris project, a giant cosmological simulation with the aim of studying the formation and evolution of galaxies. It's an ongoing project in which scientists use the most precise data and calculations currently available to create the most precise model of the universe possible. At its highest resolution, it had a volume of 106.5 cubic megaparsecs, took several months to complete on a supercomputer with 8,192 cores, used 25 terabytes of RAM at its peak, and had a particle count of over 18 billion. The simulation is detailed enough that they can actually zoom in on individual galaxies, and once the simulation arrived at present day, the result was strikingly similar to what we observe in the universe.
There's a sort of a philosophic concept that a sufficiently advanced civilization will be able to create a simulation. Yeah, maybe you've answered this before?
Beyond Planck's length, which is the real-world equivalent of a single pixel, all sense of space and distance is lost. All meaning of space and distance ceases to exist. And exactly like a computer, our time too is discrete. It isn't continuous. Time isn't one smooth directional arrow, but made up of tiny discrete packets. It acts like the processing of a very fast computer.
I've had so many simulation discussions, it's crazy.
Okay. So, because
in fact, it got to the point where basically every conversation was the AI/simulation conversation. And my brother and I finally agreed that we would ban such conversations if we were ever in a hot tub. Okay. That was like, because that really kills the magic.
Hot tub, so the idea is, right, any sufficiently advanced civilization could create a simulation that's like our existence, and so the theory follows that maybe we're in the simulation. Have you thought about this? And
a lot.
Are we
even in hot tubs? So much so it had to be banned from a hot tub. The strongest argument for us being in a simulation, probably being in a simulation, I think is the following: that 40 years ago we had Pong, like two rectangles and a dot. That was what games were. Now, 40 years later, we have photorealistic 3D simulations with millions of people playing simultaneously, and it's getting better every year. And soon we'll have virtual reality, we'll have augmented reality. If you assume any rate of improvement at all, then the games will become indistinguishable from reality, just indistinguishable. Even if that rate of advancement drops by 1,000 from what it is right now, then you just say, okay, well, let's imagine it's 10,000 years in the future, which is nothing in the evolutionary scale.
Almost every non-apocalyptic futuristic science fiction tale describes humanity as a species that will expand outwards. And maybe that's true. But when this technology turns into reality, why would you want to? A powerful virtual reality could allow us to do anything and everything. No fear of harm or death, no irreversible consequences for your actions, no physical limitations. Could that be why the universe can seem so lifeless, even though it's been around for such a long time? Perhaps every civilization that reaches a certain technological maturity realizes that expanding outwards to explore the universe is pointless when expanding inwards using technology allows you to do so much more.
So given that we're clearly on a trajectory to have games that are indistinguishable from reality, and those games could be played on any set-top box or on a PC or whatever, and there would probably be, billions of such computers or set-top boxes, it would seem to follow that the odds that we're in base reality is 1 in billions.
So
Tell me what's wrong with that argument.
Is the answer yes?
The argument is probably, but I just like, is there a flaw in that argument?
No, the argument makes sense. So the assumption then is that somebody beat us to it.
Who is the all-powerful computer programmer that presides over our virtual, relatively insignificant, self-reproducing simulation? And the most important question of all, who programmed the programmer?
No, there's a 1 in billions chance that this is base reality.
Oh, okay. What do you think?
Well, I think it's 1 in billions.
Okay.
That seems to be like clearly what it suggests.
Right.
And actually, arguably we should hope that that's true, because otherwise, if civilization stops advancing, then that may be due to some calamitous event that erases civilization. So maybe we should be hopeful that this is a simulation, because otherwise...
Because they could reboot it.
Well, otherwise, either we're going to create simulations that are indistinguishable from reality, or civilization will cease to exist. Those are the two options.
I like those odds.
Okay.
Or it's unlikely to go into some multi-million year stasis. So it's either going to increase or decrease.
It's so, in principle, easy once you have that technology to create a simulated universe that there'd be many more simulated universes than real universes. Real universes are hard to create. Maybe there's one, maybe there's a few, but it's hard to imagine that you could create them in as great abundance as you could create universes in a computer. You come home at night, you flick it on, you create a universe, you sort of kick back and you watch what happens. Because now the creator was not some mysterious being. It was some futuristic teenage kid with pimples in his garage who just created the universe. So, my question to you, what do you think about that?
Procedural content. More and more games are being built in worlds that developers created the means to exist, but didn't actually entirely build themselves. It's actually pretty amazing to think that a game like No Man's Sky is based in a universe built on math. That virtual world was created in a fashion that can actually be a little bit closer compared to how the universe actually happened. Various criteria exist within math, traits and formations and types of landscape are expressed over time. For instance, No Man's Sky uses procedural generation, like I said a moment ago, because it's impossible to even see everything in it. Can you imagine designing everything in it? You can eventually come out with an alien giraffe, or a weird tree, or a mountain, or clouds, or islands, or ships, or houses, or buildings, or urban landscapes. Essentially, if you end up putting the time into the creation of enough assets that can mathematically be combined, you can end up with so much more than simply building a world. That's in part why procedural generation is being used more and more. We're expecting larger and larger worlds from video games. And as we expect more, we definitely want to be able to accommodate that. Where it used to be for memory purposes, now it's because the human life doesn't have enough time in it to develop the size game that we kind of have in mind as a goal.
If we were to spy on the atom and see where it goes, so you put a detector just above the upper slit, that's what you get. But that's a different result to what we had earlier.
It doesn't have a definite shape or existence unless it is being looked at by something.
Leave the detector there, but just very quietly go and unplug it. Don't let the atoms know that you're not spying on them. Make them think that you're still detecting them. So, yeah, okay, we're going to run the experiment. Atoms, okay, get ready, one at a time. We're going to be checking on you. All right, so run the experiment again.
Pretty much like a video game where you're presented with the frame that you require to play. The rest of the virtual world, on the other hand, doesn't quite exist, but has the potential to be the next frame or the next level of the game.
Now, if you can explain this using common sense and logic, do let me know, because there's a Nobel Prize for you.
This means that the wave can have an energy of 3 electron volts, 6 electron volts, 9 electron volts, and so on, but it can never contain 1, 2, 4, or any number of electron volts that is not an integer multiple of 3. This is a strange result because it's analogous to saying that you can push someone on a swing by 1 foot or 4 feet, but by no amount in between. And again, the explanation for why such strange consequences didn't seem to take place in people's everyday lives is because Planck's constant, which dictates the scale of quantization, is such an incredibly tiny number.
Think of it like a flip book, only so fast that it's almost seamless.
Therefore, Planck and the scientific community as a whole regarded the assumption of quantization as a mere mathematical trick. Nobody actually believed that the quantum picture of light had any basis in reality, so nobody paid much attention to it. Nobody, except for a nameless and faceless clerk working in a Swiss patent office.
When I move this red dot across the screen, we perceive it as a smooth, sliding action. But we know for a fact that this is an illusion caused by the limitations of our sight. Nothing is really moving, it's just bits of information being modified in such a way that, from our perspective, it's perceived as motion. If we zoom in and slow down, we notice that the red dot isn't sliding as much as it snaps to each individual pixel. And this is essentially what they have observed, that the universe has a finite resolution, or an underlying lattice, as they call it. This could mean that the universe and reality is not made out of energy or matter, but is instead made out of quantized bits of information that, from our perspective, is perceived as energy and matter. The game of life. These are the rules. Number 1. Each populated cell with either one or no neighbors becomes unpopulated. Number 2. Each populated cell with 4 or more neighbors also becomes unpopulated. Number 3. Each populated cell with 2 or 3 neighbors remains populated. Number 4. Each unpopulated cell with 3 populated neighbors becomes populated. We populate as many cells as we'd like and then press play. The resulting behavior is actually quite remarkable. I mean, it's not GTA 5 or anything, but still. Cells can live, die, or multiply and create a sea of seemingly chaotic randomness. Some configurations stop immediately, while others seem to continue forever, and there is no guaranteed way of telling if any specific configuration is eventually going to stop or continue indefinitely. If we zoom out as the model continues to expand, increasingly complex patterns begins to emerge. But not only patterns, over time even the behavior changes. The interactions between individual cells is overshadowed by the behavior between entire blocks of cells. And this is the idea, that the universe began as something incredibly simplistic, like a grid of cells governed by a few simple instructions. But given enough time, it evolved into something incredibly complex. It's only natural for us to assume that the complexity of the universe must be very complicated. The world can often seem very confusing, random, unpredictable, and even unexplainable. What the game of life quite elegantly illustrates is that complexity can actually be the result of simplicity. In Maybe nothing physically exists until we observe its existence. Perhaps detail and complexity is added when it's needed instead of being constant and absolute. Perhaps discovering that this is all a simulation is part of the simulation. The world as we know it and the future we often imagine will dramatically change. When we try to imagine the distant future, we often think of humanity as these grand explorers of the universe. It's often just assumed that we will continue to expand outwards far beyond the Earth and the solar system. Of course, this is under the optimistic assumption that no apocalyptic events takes place and that we steadily continue to progress and innovate. Perhaps this isn't the first iteration of the universe and someone could be pressing the off switch right now.